Thank you very much for the presentation and for the invitation to this session, which has been very interesting for sure. As Professor Cardoso said, I'm Alejandro Gómez Yepes from the University of Vigo, and I'm going to talk about fault tolerance in multiphase electric machine drives. Okay, so this presentation is a summary of a survey paper we have recently published in the journal Machines. This journal is open access, so you can check this paper if you want further information about this subject. Okay, so multi-phase machines are those with more than 3 phases, and they present many benefits over 3-phase machines, like, for example, a smaller current rating for the same voltage and power rating, as well as reduced ripple in the torque in the DC link voltage. And thanks to the additional number of degrees of freedom, these machines permit to obtain a higher degree of fault tolerance and a higher torque density. And they also enable other functions that are in principle not easy to obtain with three-phase machines, like multi-motor drives, bearing-less machines, integrated battery chargers for electric vehicles, etc. And for these reasons, these machines are becoming very strong contenders for several applications, especially for those that mean a greater requirement of reliability, like some kind of electric vehicles and some other applications, like, for example, remote wind energy farms, where it is desired to have low maintenance. Okay, so as you know, an AC drive is composed of many different parts that are susceptible to faults, like the converter modules, the connections between the converter and the machines and the machines themselves. So when a fault occurs, it's very important in the first place to identify the type of the fault that takes place in order to apply the most adequate tolerant action. There are also some fault-tolerant methods that do not require diagnosis and reconfiguration, but with them the performance is not optimum, so they can be used during the transient while the diagnosis is performed. Among all these faults, most of the literature regarding multi-phase machines are focused on the particular case of open circuit faults, especially the faults that mean that a phase is in open circuit, which means that there is no current at all through a phase. So most papers are focused on this case, which can be caused, for example, by an open circuit fault in a connection between the machine and converter, or an open circuit fault in a stator phase, or many times there are other kinds of faults that are converted into phase open circuit faults as well, for the sake of simplicity and safety. Like the ones that are indicated by green blocks. In some cases, that they are converted into phase open circuit faults. However, the problem is that if this is done, then you are reducing the number of current degrees of freedom, and as a consequence, you have a lower performance because the achievable torque is reduced and the losses are increased for the drive. So in the literature, this kind of conversion into phase open circuit faults is often applied, for example, for the case of failures in the switches in the current sensors. Sometimes in the case of a fault in a converter module, because the entire converter module can be isolated and converted into open phases. And also sometimes in the case of high resistance connections. In any case, as I said, sometimes it's better not to do this conversion in order to obtain better performance by applying a specific kind of fault tolerant method that is specific to that particular kind of fault. In the literature about multi-phase machines, there are also a lot of papers that are focused on the case of short-circuit faults in the stator windings. And in some cases, this is treated similarly to the case of a switch short circuit by increasing the impedance of the machine stator. And in the rest of the presentation, we will focus mainly on these faults, the one that are the most common in the literature. So, but anyway, in the literature about multiphase machines, there are also many papers about many other kinds of faults that can occur in a multiphase drive. So if you want further information about that, you can check our survey paper, for example. And in this regard, it is also worth remarking that the increase in the number of degrees of freedom that is found in multiphase machine implies better performance in terms of tolerance and diagnosis, not only to the faults that affect individual phases, like an open circuit in a phase or a short circuit in a phase, but also, in fact, is better performance for most of the fault types that can occur in a drive, even for those that affect the drive as a whole, like, for example, an encoder fault, thanks to the increased number of degrees of freedom. So, as I said, the open circuit faults are the most widely studied in the literature. They can be caused, for example, by an open circuit fault in a connection in a stator phase, or by conversion of other faults into them. These faults can be detected before the tolerance by model-based, knowledge-based, or signal-based methods, but usually signal-based ones are preferred because they are simple and also less sensitive to model parameters. So most of the papers use signal-based methods in multiphase machines. It's also very interesting to note that there are some papers during the last years on the subject that have shown that multiphase machines make it possible to obtain diagnostic methods that are faster and more robust than in three-phase drives. This is because the vector space decomposition transform in multiphase machines gives rise to different subspaces that are in principle decoupled. So this makes it possible to achieve better and a faster diagnosis than in three-phase machines, and quite often. Not only for open circuit faults, actually, but for most other types of faults. And some of the open challenges regarding the diagnosis of open circuit faults are the discrimination from other faults. There are already some papers about this, but not many. And also the addressing the case of multi-level topologies, because depending on the particular switch that is faulty, the behavior is not the same. And most of the papers are focused on the case of two-level converters, not multi-level topologies. So that's an open challenge yet. Regarding tolerance, there are many methods in the literature regarding this subject, and it's possible to obtain tolerance by reconfiguring or not the control and the drive topology. But most of the methods actually assume that the drive topology is not reconfigured for simplicity, and that the control is actually reconfigured for the best performance. Regarding the reconfiguration of the post-fault control, it depends on the type of controller. It's not the same. I mean, if you have a predictive control, for example, the reconfiguration will be different from the reconfiguration if you are using a proportional integral controller, for example. And also the vector space decomposition transform that you are using for the controller can be reconfigured or not. But most of the literature actually keeps the same full order vector space decomposition transform as in healthy machine when the fault occurs. This is preferred because in this manner you avoid modifying the transform. You also have a good insight about the space harmonics that are in each specific machine plane, machine subspace. And also you have a reduced coupling between the machine subspaces. When you are defining the optimum current references after the fault occurs, you have to take into account several constraints. Of course, some of the currents are zero, and you have to take that into account. And also, in order to avoid damaging the drive, you have to limit the currents. And there are different criteria in order to limit the current in order to avoid the damage of the drive. One of the possibilities is to take into account the current RMS rating in each of the phases so that none of them surpasses it. Also, it's possible to take into account the peak current limit to avoid exceeding the converter output voltage, the maximum converter output voltage, to avoid causing saturation of the machine flux, to avoid exceeding maximum local temperature, among other possibilities. But most of the papers are focused on limiting the current to the phase current RMS because it's easier to do and also it's safer because it's more conservative. Also, in order to obtain the optimum current references, it depends on whether you have space harmonics or not. If you disregard these space harmonics, the conventional methods from several decades ago were usually classified depending on whether you are trying to minimize the losses or to maximize the achievable torque of the machine. But actually, in the last years, it has become more popular to apply the so-called full range minimum loss strategy, which combines the advantages of both methods because it's able to ensure minimum losses for each torque value in the entire torque range. So it's better than the previous two, and it's becoming increasingly popular. Also, if the space harmonics cannot be disregarded, then the torque ripple caused by the interaction with the space harmonics also needs to be taken into account when calculating the optimum current references. And some of the open challenges regarding the tolerance of open circuit faults are, for example, the design of reconfigurationless fault-tolerant methods. There are already some fault-tolerant methods that do not require diagnosis and reconfiguration, but the performance when you use this method is not still as good as with the fault-tolerant methods that rely on reconfiguration. So this is still an open challenge. It is also a recent trend because there are some improvements in performance with this method, but they are still not as good as the other ones based on diagnosis. So it's an open challenge. And also there are some recent trends that try to exploit all the healthy switches of a drive with faults. Also those that are in the same legs, in the same converter legs as a switch that has suffered a fault. So new papers have shown that it is better to actually keep using those switches in order to obtain better performance. And this becomes especially interesting in the case of multi-level converters, which has been barely addressed so far. And of course, it's also interesting to try to extend these methods to other kinds of faults, because as we said, the open circuit faults are the most widely studied, but these methods, many of these methods have not been extended to other types of faults yet. And another important kind of fault are the short-circuit faults in the stator windings. They are very troublesome because they tend to cause very large current, especially when the short-circuit fault involves just a few turns because the impedance is very low. These faults can be caused by different kinds of stress. They can be detected by methods similar to those used in three-phase machines, but there are also some papers that have shown that it's actually better to try to exploit the particular features of the current in the multi-phase vector space decomposition subspaces, which offer better properties. Regarding the tolerance, most of the papers on the subject are focused on designing synchronous machines specifically by using fractional slot concentrated windings or multiple three-phase sectors in the stator. They try to increase the impedance of the stator so as to limit the short-circuit current, and also in order to obtain a high degree of isolation between phases or between stator sectors. There are also many methods that are based on the drive topology and sometimes its reconfiguration. For example, some of the oldest methods on the subject were based on applying an external short circuit to the terminals of the phases affected by the fault. And sometimes a zero sequence path for the current was also provided through the converter topology. In this manner, when the short circuit fault occurs, it tends to induce a current that naturally tends to reduce the flux linkage through the shorted turns. And this causes that the short circuit current is reduced. This is effective, but however, these degrees of freedom are not really exploited. They are not controlled actively. So the performance is not as good. So more recently, some other papers have tried to keep actively controlling as many degrees of freedom as possible instead of applying external short circuits. So it's better to keep using all the healthy switches that the drive still has and to use a proper current control. And some of these methods, for example, are focused on minimizing the short circuit current, and some others are focused on minimizing the torque ripple after the fault. But most of these methods do not take into account both goals at the same time, so that can be considered a very interesting open challenge, I think. And also there are some other methods that are based on introducing additional devices within the machine, but they are costly and complex, so they are usually not employed in multi-phase machines. And there are also some other open challenges. Like, as I said, it would be interesting to try to extrapolate the methods from phase open circuit faults to the case of short circuit faults, like, for example, the full branch minimal loss strategy, or, for example, the methods that do not require diagnosis and reconfiguration. Also, the case of short circuit faults between turns of different phases has barely been studied so far. And also the design of induction machines able to withstand this kind of faults is still a pending task. I don't know if it will ever be possible, but it's still a pending task. And also, you can also have short circuit faults in the switches. They can be caused by stress or by faults in the gate voltages of the switches. They can be detected by monitoring the on-state voltage drop of the switches or the stator current in the multi-phase and subspaces of the machine. The methods that are based on designing the machines in order to increase the stator impedance can also be used to a great extent for these faults, because they are able to reduce the current produced by the short circuit faults, not only the stator faults, but to a great extent also the switch short circuit faults, okay? And there are also some other methods that design control and modulation techniques depending on the specific switches that are faulty. And there are many methods that address the drive topology. Some of them are based on using redundant legs, as in three-phase machines, but this is not really used in multi-phase machines because you don't need it. You have redundant degrees of freedom and you don't need to use redundant legs, which are costly. One of the most common methods to tolerate these faults is to convert them into phase open circuits by isolating the corresponding converter leg from the machine. But in this manner, since you are reducing the number of current degrees of freedom, then the achievable torque is reduced and the losses are increased. Although the good part is that you have a better DC link utilization, which can be useful for reaching high speeds. Another disadvantage is that you require additional devices in order to provide the isolation of the faulty switch or leg. There are some methods based, for example, on modular voltage source converters, like using an edge bridge for each of the stator phases. And this approach does not require to isolate the fault because you can still have current through the faulty switch. However, in this manner, there is a problem because you have a zero sequence path that is excited by default, and then you have an uncontrolled zero sequence current that increases the losses, and this is undesired. This is different from the case of stator short circuits because for stator short circuits, as we saw in the previous slide, the induced current tends to reduce the flux linkage in the sorted turns of the machine. But this is not the case for switch short circuit. So in this case, it's better not to have zero sequence paths, okay? One method to avoid the zero sequence current would be, for example, to have multiple three-phase converters. And then if a fault occurs in one set, then you could apply a three-phase short circuit to that set. So in this manner, you don't have zero sequence current. But the problem is that you are losing these degrees of freedom that you cannot actively control. This is another kind of topology where you use a half bridge of n phases at each side of the machine, provided it has open-end windings. So for example, if you have a short circuit in this switch, you can set the other switches of the same phase in this manner, and then you can still have current flowing through the affected phase at all times. This current depends on the current through the other phases. So you can control the current in the affected phase through controlling the other phases. So in this manner, you have controlled current through all the phases of the machine, and hence you have a very high achievable torque. Actually, it can be as high as for a healthy drive because you have controlled current in all the phases. The problem is that the DC link utilization is worse compared with the isolation of the affected phase. This is a similar approach for the same topology in which you create a virtual neutral point at one of the sides. So in this manner, you also have controlled current through all the phases without zero sequence. And also, the problem is that you have a slightly worse DC link utilization compared with the previous case. And of course, compared with the conversion into phase open circuit. Another possibility is if you are using a conventional n-phase half-bridge converter, another possibility is to then isolate the faulty switch, for example, by a fuse or some other device, and then you could connect the affected phase to the DC link midpoint so that you can have current through that phase, and this current depends on all the other currents, so it can be controlled through them. In this manner, you have again controlled current in all phases, and hence better achievable torque and lower losses. But again, lower DC link utilization than by isolating the affected phase entirely. So this solution is very good for low speeds, but not for high speeds because of the limit in DC link utilization. So it has been recently proposed, for example, to use this approach for low speeds and to isolate the phase at high speeds. So in this manner, by using this at low speeds and this other option at high speeds, you have extended torque speed range, which can be convenient. And yeah, perhaps this solution could be further investigated for other cases. And also, I think it is particularly interesting the case of multi-level converters because they provide switch state redundancy that can be exploited for tolerance to these faults, and it has barely been studied so far, just for a few very specific topologies like T-type converters. but not for most other multi-level topologies. So I think that's quite interesting. So I will summarize some conclusions based on this presentation and also based on the survey paper we have recently published a few months ago. Okay, so we have seen that most of the papers in the literature address the case of phase open circuit faults. Secondly, there are also many papers that address stator short-circuit faults. In addition, there are many papers that address the case of fault tolerance for other faults in multi-phase machines. And these other papers have shown that the extra degrees of freedom of multi-phase machines enable better performance for the fault detection and tolerance, thanks to the additional subspaces and their decoupling. And this is not only regarding the phases that, I mean, the faults that affect individual phases, but also most other fault types, even those that affect the overall drive, thanks to the additional degrees of freedom and VSD subspaces. For example, you have less torque disturbance, even if you inject a signal in the secondary subspaces for the diagnosis or for the tolerance. Also, you have easier discrimination between faults because they are mapped into different subspaces that are in principle independent from each other. You have better signal to noise ratio because most of these subspaces have very low impedance, and also they are independent from the subspace of the fundamental. So it's easier to have a clean signal for diagnosis or also for tolerance, because there are some tolerant methods that rely on measuring signals, like for example the tolerance to encoder faults, where you can measure, for example, the rotor slot harmonics, or you can inject high frequency signals into the secondary subspaces. Another interesting conclusion that we can draw is that even though converter modularity was traditionally assumed to be always better for fault tolerance, this is not always true. There are some cases where this is not the best solution. For example, if you split the stator phases, you are actually reducing the number of current degrees of freedom, and hence you are reducing the achievable torque, and you are increasing the losses for the same torque value. Also, if you are using independent H bridges for each phase, you are providing additional zero sequence paths that can be excited by a short circuit in the switches, causing uncontrolled current that increases the losses and the current per phase. And in addition, in this manner, you are worsening the DC link utilization, which also means worse tolerance in the face of the faults that decrease the DC link voltage. Because of this reason, there are some recent papers in the last years that propose to, for example, to reconfigure the drive depending on the fault, so that you can adjust the degree of modularity to obtain the best degree of modularity depending on the fault. Of course, this has the inconvenience that you need extra devices for the reconfiguration. So it's a trade-off depending on what you prefer. Some other interesting conclusions that we can extract from the literature is that the conventional traditional method of applying terminal short circuit in order to tolerate short circuit faults is not the best in terms of performance, because again, you are losing current degrees of freedom that you are not fully optimizing. And the same occurs if you are isolating an entire leg when there is a switch fault. So the new trends show that it's better to keep exploiting using all the healthy devices of the drive instead of isolating the entire leg when there is a fault. there's also it's also interesting to keep trying to improve the performance of the fault tolerant methods that do not require diagnosis and reconfiguration, because the current ones that we have do not provide as good performance as the fault tolerant methods that do not rely on that do rely on reconfiguration. So it's better to keep trying to improve the performance of these methods. Also to try to extend the methods from open circuit faults to other kind of faults, and to design the fault diagnosis and fault tolerant methods considering many types of faults at the same time, which is usually not done in the literature. Also, we have mentioned that it would be good to try keeping investigating the tolerance of multi-level topologies, exploiting the switch state redundancy, which is not really done in most of the papers, to try to achieve simultaneous minimization at the same time of the short-circuit current and the torque ripple in case of stator short-circuits, to try to better exploit the actual capability of multiphase drives in case of faults, because most of the papers assume that the phase current RMS is the actual limiting factor for the torque, but that means severe derating of the drive. It's better to keep trying to actually exploit better the capability of the drive. Also, it's interesting to try to design induction machines really tolerant to stator short-circuits. And also, almost most of the methods that are aimed at fault tolerance do not consider the possibility of using the degrees of freedom for other purposes at the same time. And it's interesting to keep this possibility in mind when designing the fault tolerance, because it would be useful to use these degrees of freedom also for other purposes while having fault tolerance, like increasing torque density, multimotor drives, bearingless machines, integrated battery chargers, etc. Okay, so I think this is all. Okay, so thank you for your attention, and I will be glad to answer any questions that you may have.
Thank you, Dr. Jeps. We are already 10 minutes late, but I still see a couple of questions in our Q&A box. So I will really ask for your capacity of synthesis in trying to answer to these two questions. I'll try to read them together, and then you will take them just to give a short answer. I apologize for that, but we need to move on. So first question is, first of all, to say thank you to you for this interesting presentation. It's from Omar Bouyaya. And the question is how the performance of the machine is increased in degraded mode, like phase losses, knowing that the degrees of freedom are reduced by losing the phases. So how the full range torque with minimum loss can be achieved in this case? And the second question is coming from Bassam Abdelmajid. Thank you, Dr. Alejandro, for this excellent and very informative presentation. I have a question regarding multi-phase drives. From the overall drive performance point of view, what is the most promising phase number in multi-phase electric drives? Please.
Okay, thank you for reading the questions and for the questions. Okay, so in the first place, regarding the question by Omar, thank you for your kind words. Okay, so when you have a fault scenario, you have to take into account the constraints of the fault scenario that you have to see which particular phases are faulty and define those constraints in your optimization problem. And then you can run your optimization problem by different optimization techniques. For example, I use the fmincom command in MATLAB, and I think it gives very good results. So I suggest you could use that one, for example. But first, you need to define well the current constraints depending on the fault scenario that you have, and depending on the on the limiting factor that you want to take into account for limiting for avoiding the overheating of the drive, for example, the phase current RMS. Okay, I hope that that answers your question. And regarding the other one, thank you, Basam. Yeah, that's an interesting question indeed. I would say that most people tend to prefer the six-phase machines. This is because of several reasons. On the one hand, you have the main advantages of multi-phase machines because you already have several extra degrees of freedom compared with three-phase machines, typically 2 or 3 degrees of freedom. And also it's quite convenient because it's a multiple of 3, so you can just buy 2 three-phase converters, which are usually available in the market. And also, yeah, I would say those are the main options, because if you try increasing the phase number, also the complexity keeps increasing. So sometimes it's not as convenient. I mean, the performance is better, of course, if you keep increasing the number of phases, but also the complexity. But perhaps you don't really need to increase the number of phases too much. So I would say that 6 perhaps a good number.
Okay, thank you, Dr. Yepes. I'm sorry, we have to conclude here, even because the staff is telling me that we don't have any more time. So thank you once again for your very comprehensive presentation. Thank you.